So here's problem number 23 from section 9.3. We're going to use the remainder estimator theorem. Let's remind that this absolute value of the remainder has got to be less than some magical number m multiplied by x minus a to the n plus 1 power, all divided by m plus 1 factorial. So there's the theorem written out. And we need to find the magical number m, which is based on what is missing, the next derivative after the polynomial that we're using to do the estimation. So in this case, we're estimating e to the x using the second order. So we're going to be using the third derivative of e to the x. Well, it just so happens that if f of x is equal to e to the x, the third derivative of this is still just e to the x. All right? Now, the next thing we need to say is, based on that n plus 1 derivative, what's the largest value that that function takes on the interval that we're interested in? Now, the interval that we're interested in is described right here. That absolute x has got to be less than 0.01. In other words, here's 0, here's negative 0.1, and here's positive 0.1. And so we're anywhere on that interval. So let's look at that, think of that function on that interval. What's the largest value that the e to the x function that n plus 1 derivative has? It's going to have it at 0.1?
Yeah.
Okay. So we're going to say that m is going to be the value of e to the 0.1. The largest value the n plus 1 derivatives has on the interval of interest. All right? So let's fill that in. The remainder has to be less than e to the 0.1 multiplied by x minus a to the n plus 1 power. In this instance, what is a? Well, that Taylor series representation of e to the x is centered at 0, so a is 0. So really we're just talking about x to the n plus 1. Now what value are we going to use for x? The 0.1. So this is going to become 0.1 to the third power. And again, n is 2 because it's a second order polynomial. Right? And then lastly, divide by 3 factorial. Now, we're going to calculate this. Let me get the calculator out. Go to the large screen for a second. Move this over to the side. All right. So I'm going to put in e to the 0.1 multiplied by 0.1 cubed, and then I'm going to divide that whole thing by the 3 factorial, which is what, 6? And I get 1.842 times 10 to the negative 4. And you can see that that's the same error that they gave. Now, that being said, we were able to achieve the answer that's in the book. Okay. Truth be told, if we were using this function to estimate the value of e to the 0.1, and we want to know how big our error was, it's unlikely that we would actually use e to the 0.1. We really wouldn't know what e to the 0.1 was. I don't know if I'm making myself... it's like we're using the thing that we're trying to find the error for by using the actual value. There's sort of a contradiction in there. Okay, so oftentimes, instead of using exactly e to the 0.1, we would use like an estimator of the value of e. Maybe 2.72, just a little bit higher than what we know e to be. All right, but we would be around there. But this gives us that exact answer. Okay, is that a good rounding out of that? All right, great.